Hey everyone, welcome to this explainer. I am absolutely thrilled to have you here today. We're going to embark on a little journey into what honestly feels like the foundational black magic of computer science. We're talking about the underlying logic of exactly how computers organize and process information. If you've ever sat there and wondered, how does Google find your exact search term in milliseconds? Or how does your GPS calculate the absolute fastest route home before you've even put the car in drive? Well, you are in exactly the right place. Today, we're demystifying data structures and algorithms. We're opening up the literal toolkit that makes all modern software possible. To really grasp the high stakes of what we're talking about here, think about this quote for a second. Using the proper data structure can make the difference between a program running in a few seconds and one requiring many days. Seriously, that is not an exaggeration. Understanding these concepts is pretty much the ultimate superpower for any programmer. Because you're not just writing code that kind of works, you're writing code that scales, code that's elegant, and most importantly, code that doesn't completely crash when a million users suddenly decide to log on at the exact same time. Okay, let's dive into our blueprint for today. Here's the agenda. First, we'll cover the foundations of computer science. Then, we'll look at measuring efficiency with Big O. Third, essential linear data structures. Fourth, we'll get into trees, networks, and graphs. And finally, we'll wrap up with the limits of computation. Starting off with Section 1, Foundations of Computer Science. Look, before we can start building anything meaningful, or even reach for a specific tool in our kit, we've got to agree on what these tools are actually doing, right? We need to get our terminology straight. And it all begins with a problem. Now, in computer science, a problem isn't actually a bad thing at all. It's simply the goal we're trying to achieve. You can think of it as a mapping of your inputs to your matching outputs. For example, sorting is a total classic. Your input is just a scrambled, chaotic list of numbers, and your desired output is that exact same list, perfectly ordered from smallest to largest. Notice how the problem definition doesn't tell you how to sort it, it just clearly defines what success looks like. So, the actual solution to that problem, that's our algorithm. An algorithm is just a reliable, step-by-step recipe that the computer follows to get the job done. But, and this is key, it can't just be any sloppy recipe. It has to be totally correct, composed of very concrete, unambiguous steps. And crucially, it must be finite, meaning it actually has to finish at some point and not just spin out in an endless loop forever. Which brings us to the final piece of the foundation, the program. So if an algorithm is this abstract idea, like a brilliant recipe you've just got mapped out in your head or scribbled on a whiteboard, the program is that exact recipe translated into a specific programming language. We're talking Python, Java, C++, whatever it is that the computer can physically execute. The algorithm is the pure logic, the program is the physical reality. So how do we systematically build a truly great program? Well, we use a pretty logical three-step methodology. Step 1, analyze the basic operations your problem actually requires. Like, are you going to be searching for data a lot or mostly adding new data? Step 2, quantify your resource constraints. Ask yourself, how much memory do I actually have to work with, and exactly how fast does this need to run? And then Step 3, select the specific data structure that best meets those exact requirements. All right, moving right along to Section 2, measuring efficiency with Big O. Because look, once you've figured out your problem, you really need a rock-solid way to evaluate if your chosen recipe is actually any good. We need a universal measuring stick. So let me ask you this. How do we measure the efficiency of our tools? I mean, we can't just pull out a stopwatch and measure it in raw seconds. Why? Because a massive supercomputer is always going to run a terrible algorithm faster than an old, clunky laptop will run a brilliant one. We need a way to measure the inherent efficiency of the algorithm itself, completely independent of whatever hardware it's running on. And that is exactly where asymptotic analysis comes into play. Enter Big O notation. This is our universal measuring stick. It beautifully shows how changes in your input size, which we usually just call n, affect the processing time. So an O of 1 algorithm, that's incredible. It takes constant time whether you're dealing with 10 items or 10 million. O of n is linear, meaning if you double the data, you double the time. Totally reasonable. But look down O of 2 to the n at the bottom. That is an exponential growth rate. If you write an algorithm with exponential complexity, it's going to become prohibitively expensive super fast. We're talking about taking years to compute even modestly sized inputs. It's wild. Now, when we're analyzing these algorithms using Big O, we also have to decide which scenario we're actually looking at. We could look at the best case, where the stars align and everything goes perfectly, but honestly, in the real world, that's almost always way too optimistic. Instead, software engineers rely on the worst-case scenario. By looking at the absolute maximum resources an algorithm could ever possibly need, we can make solid engineering guarantees about its performance. No matter what crazy input a user throws at the software, we know for a fact it's not going to crash or freeze on us. Okay, Section 3, Essential Linear Data Structures. Now that we know how to measure our tools, let's actually start pulling them out of the toolbox. We're going to shift gears here and look at the most basic yet absolutely essential tools in a programmer's belt. First up, let's compare the two absolute titans of data storage, arrays and linked lists. Arrays store their data in contiguous, side-by-side memory blocks. Linked lists, on the other hand, use little pointers to link totally scattered pieces of data together, kind of like a chain. So what's the trade-off? Well, arrays give you instant O of 1 access to any specific item. It's like knowing exactly which PO box to open. Linked lists are a bit more like a scavenger hunt. You get incredible flexibility to dynamically resize and add new clues, but you do have to slowly follow the chains step by step to find what you're actually looking for. Building right on top of those, we've got stacks and queues. These are all about the specific order in which data is processed. A stack is quite literally exactly like a stack of plates in a cafeteria. It uses a last-in, first-out, or LIFO system. The very last plate you put on the top is going to be the very first one you take off. A queue, though, is perfectly modeled by waiting in a checkout line at the grocery store. It's first in, first out, or FIFO. The very first person to get in line is the first person served. They're super simple concepts, but they are incredibly powerful for managing tasks inside a program. Moving on to Section 4, Trees, Networks, and Graphs. Let's see how our toolkit handles much more complex, massive amounts of interconnected data, because sometimes a simple straight line just isn't going to cut it. Imagine a beautifully organized hierarchical structure called a binary search tree, or BST. In this setup, every single node branches out into two paths. Anything smaller goes to the left, and anything larger goes to the right. And why is this such a game changer? Because every single time you make a decision to go left or right, you instantly eliminate half of the remaining data. This elegant splitting logic gives us logarithmic, O log n, search time. Literally, this is exactly how your smartphone can find a single contact instantly out of thousands of names without even breaking a sweat. Of course, reality gets pretty messy. So, computer scientists have invented some brilliant, advanced variations to guarantee things stay fast. First, you've got AVL trees. These are amazing because they automatically self-balance, so they never devolve into a slow, lopsided line. Then there are heaps, which are perfectly designed for priority queues. They always keep the absolutely highest priority item right there at the top. And finally, B trees, which are specially optimized with multiple children per node just to handle massive databases stored on those slower physical disk drives. The point is, every single one of these was meticulously invented to solve a very specific time or space constraint. But hey, what if you don't even want to bother searching through a tree at all? Enter the hash table. You can think of this as the ultimate shortcut. It uses a bit of math called a hash function to instantly map a key, let's say a user's name, to a very specific slot in memory. It gives you near instantaneous O of 1 direct access. Now, the only catch is that sometimes two totally different keys hash to the exact same slot. We call these collisions. It's basically like when three guys named Matt all walk up to the barista when a coffee order is called out. Managing those collisions cleverly is the actual secret sauce to making hash tables work so remarkably well. And when data is just highly interconnected, we pull out a graph. A graph is essentially a network made up of vertices or nodes that are connected by edges. This perfectly models real-world complexities. Think about stuff like family trees, city road networks, or even who follows who on social media. Those are all graphs. And to navigate them, we use really specific traversal algorithms. You've got breadth-first search, which explores outward layer by layer, or depth-first search, which dives as deep as humanly possible down one single path before finally backtracking. Finally, we reach Section 5, the limits of computation. Look, we've explored some genuinely incredible tools today, but reality dictates that not everything has an easy fix. Let's talk about the absolute limits of what computers can actually do. Because you have to wonder, what happens when a problem is simply too hard, too complex for any algorithm, any clever data structure, or even the most powerful supercomputer on the planet? It's a bit of a sobering thought, but computers do actually have hard mathematical limits. This brings us to the absolutely fascinating realm of NP completeness. We are talking about a class of incredibly hard problems that demand exponential time. Take the famous traveling salesman problem, for instance, where you're trying to find the absolute shortest possible route connecting a dozen different cities. With these kinds of problems, if I hand you a potential route, you can very quickly check the total distance. Easy. But to confidently calculate and find the perfect shortest route from scratch, that takes so mind-bogglingly long for large data sets that, honestly, the best approach might just be making a really educated guess. Which brings us to the unifying theory that summarizes this entire explainer, the space/time trade-off. This right here is the universal golden rule of computer science. If you want blazing fast execution time, you usually have to buy it by using up significantly more memory to store shortcuts and indices. Conversely, if you're tight on memory and need to save it, you have to pay for that by accepting a much slower running time while the computer calculates things on the fly. You almost never get both. Software engineering is really just the art of balancing those two competing forces. So we've seen today that every single data structure, every algorithm, and every design choice you make carries explicit costs and massive benefits. You now understand the blueprint of how software actually thinks. So I'm going to leave you with this. The next time you sit down to write a program, or even just look at a new piece of technology, view it the way a master craftsman views their toolkit. Every problem has an elegant solution out there. The question is, which tool will you choose next?